We're moving on to our last session of the day. It's been a great day filled with lots of informative presentations. We want to thank all of our presenters for being here and thank you too for joining us. Just to remind you, we are taking questions throughout the presentation. Submit them through the questions tab located at the top of your screen. And if we don't get to your questions during the presentation, someone from the Neo4j team will reach out to you directly. Without further ado, I'll hand the floor over to Lance Walter, who will introduce our last speaker of the day. Again, thank you so much for joining us. We've really enjoyed you being here.
Yes, thank you all for taking some time out of your busy schedules to be with us. We do appreciate it, and we hope you've gotten a lot of value out of the program so far. As I promised at the outset, we're going to wrap up with a really fun, high-energy session. Mats Rydberg is a software engineer here at Neo4j, based out of our engineering center in Malmö, Sweden. Mats holds a master's degree in computer science from the Faculty of Engineering at Lund University. Mats has held multiple software development positions since then and has spoken at several Neo4j events, so maybe you've seen Mats before. He's a Neo4j veteran. He's been with us for more than 5 years, and in his current role, Mats leads our engineering efforts around graph data science and Cypher for Apache Spark. This should be a really fun session to wrap up the program. While the graph data science library is new, graph algorithms aren't. And our team has learned a lot over the years about best practices. And in that spirit, Mats is going to share worst practices from what we've learned to help you avoid some common pitfalls. Welcome, Mats.
All right. Thank you very much, Lance. Yes, welcome everyone to this final session. My name is Mats, and I'm coming to you from Malmö, Sweden. It's sunny and nice. I represent here the Graph Analytics team, the engineering team behind the GDS Graph Data Science Library. We're the people who actually write the code, the tests, and design the APIs together with our product management team. And I'll just get going. So a little bit about me. This is me sitting in a nice restaurant in Amsterdam. I've been with Neo4j for about 5 years. And the last year, I've been focusing in on our team that I belong to, have been focusing in on graph data science in particular. So in this session, I will teach you, or I will present to you a number of common issues that we've seen. So while, as Lance said, the GDS library is new, graph algorithms aren't. In fact, the graph algorithms library, differently named, but with much the same contents, has been live out there for working on Neo4j and supporting the community for quite some time. During that time, we've been able to collect a bunch of knowledge about what works, what does not work. And this session will be focused on some things that we know does not work. So I'll try to convey these experiences to you in the best way that I can, and also give you the best recommendations that we have to avoid these mistakes. So the first and longest part of this session is going to be formatted along the lines of the slide. There's going to be a quote, a citation here for some imagined or actually experienced problem for users of our library, and then some recommendations that I'll talk to for how to avoid them or best deal with them when they happen. First up then is Neo4j crashes when I put the jar in the plugin directory. And this often comes down to version compatibility mismatch. Either the Neo4j version is wrong or the GDS version is wrong. In any way, they don't work in the combination that was attempted. So one thing to keep in mind here is that GDS 1.0 and 1.1 supports Neo4j 3.5.9 and later 3.5 versions, but not 4.0. Conversely, GDS 1.2 supports Neo4j 4.0, but not 3.5. So make sure that the right GDS version is used based on what Neo4j version you're using. Similarly, like I mentioned, the graph algorithms library is not compatible with graph data science. That one works for even older versions of Neo4j, for some of its versions. But in the 3.5 series, there's a bit of an overlap. So make sure you only have one of those libraries installed at a time or it won't work. Moving on, I can't find feature X right? You've been watching this webinar, you've heard about all the nice features, or you read the documentation, and you're looking to try something out, and you can't find it. It doesn't work. You get weird errors. Well, make sure you're using the latest GDS version. It should have all the features. You can upgrade in UVDA Desktop. There's a plugin to manage the GDS library. You can also download directly from the download center, where you can also see which the latest version actually is. If you're reading the documentation and you're using that to try out the features that are documented, sometimes you will have in the URL an actual version number that indicates what version of the documentation that you're looking. So make sure that that is the version of the documentation version you're reading is the one that corresponds to the GDS version that you're using. Here's 4 versions of really the same thing. Like my algorithm ran, but it returned all zeros, or it ran, but the results are all the same, or it ran, but every node is in its own community for community detection algorithms, or it ran, but the shortest path is infinity, which isn't very short, is it? Now, results like these, they sort of indicate that the algorithm hasn't done anything. All the nodes in the graph, they remain in their initial position, their starting position. So when an algorithm starts to run over a graph, usually what it does is for every node in the graph, it considers the relationships of that node, of all the nodes. And it traverses the relationship over to the neighbor of the node, or all the neighbors. And if a node doesn't have any relationships and thus doesn't have any neighbors, we call this an isolated node. It doesn't have a connection. Usually those nodes aren't useful. This relationship traversal, it forms the basis of computation for almost any algorithm. And an isolated node is, once found, just left. It isn't interesting, and the algorithm continues on executing for the other nodes in the graph. And if you find that it sort of left all the nodes in the graph in their starting position, like initialized to 0 or in its own unique community, then probably there aren't any relationships, or that could very well be the case. So if you have a graph with only nodes and no relationships, that isn't much of a graph. It looks more like a table or something. So check your projections, check your graph, see if it actually corresponds with the input that you were expecting the algorithm to run over. Did you perhaps project the wrong relationship type and you didn't get any connections in your graph? And this is sort of the other side of the coin, or the other side of the scale. My algorithm ran, but all the nodes are in the same community. Right? Instead of having every node in its own little community of 1, you now got all the nodes in the entire graph clumped up into one big community. Neither of those ends of the scale are very useful typically. You want to be somewhere on the balance in the middle there, or not in the middle, but on one side of the spectrum. And in this case, it may be that your graph is too densely connected. Rather than there being no connections in the graph, there's now too many. Like your graph could be fully connected. And then it's difficult for the algorithm to determine where to break up these connections into different sets. But maybe you were doing this and you got these results from a particular community detection algorithm. Then I'm happy to inform you that there are other community detection algorithms that you can try instead. So if you try WCC, maybe you can try label propagation or Louvain. And they are all production quality algorithms with the highest level of support. So I can safely recommend using any and all of them. And you can configure them a little bit differently. You can use weights, or you can use thresholds. Thresholds is a WCC feature that allows you to skip some relationships that are of a not as interesting. So instead of just using the mere existence of a relationship, you use a heuristic to exclude some relationships from the graph that the algorithm considers, and thus reducing the the dense connections to a slightly more sparse view of the graph. And maybe it gets easier for the algorithm to break it apart into communities at that point. Also, if you're using Louvain, you can check the intermediate communities to see the progression at which the algorithm is trying to identify the various community sets. And if you've overcome these obstacles, your algorithm produced, let's say a community detection produced a community distribution of some sort. It's not everything in one, and it's not everything on its own. It's somewhere in between. It looks right. Okay, I'm done. Things are great. Right? Not necessarily, unfortunately. So the algorithms, they are complicated sometimes. They are defined over sometimes quite a narrow use case, but that narrow use case is always a graph. So if there is a graph as an input, the algorithm will happily run over it. It doesn't know that the nodes that it gets to see in the graph actually represent real life things that aren't the same. So you're mixing pears and apples, or apples and oranges. Pears and apples, that's a Swedish expression. So if you have a graph with persons and items, stores and countries, these are different things, but you can put them all in one graph, and you have person lives in country and person buys item, and item exists in store. Store also exists in country. These are different kinds of relationships between different kinds of entities or nodes. And they aren't the same. When you run an algorithm over it and you try to do a community detection algorithm, you want to do that over things that represent the same thing. You don't want to try to community detect people and countries or stores and people. You want to do it with people and stores, perhaps. So it's possible to project a bunch of differently typed nodes into the same thing and let the algorithm believe that they are. And the algorithm will not tell you that they aren't the same because it doesn't know. Similarly, you can treat anything, any number, as a weight, even though it isn't actually representing a weighted thing. Maybe it's just a number for unique identification, like a social security number or a line item number for a product. Then those things are not going to be interesting as weights. So make sure that the weights that you're using are actually weightable things that to compare, like I'm rating a movie at a particular strength, like 3 out of 5 or 4 out of 5, then that is probably good as a weight. And speaking of weights, like some algorithms are weighted, which usually is a good thing. It enables you to inform the algorithm a little bit more about the more fine-grained details of your data. But most of them that are weighted also can run in unweighted mode. And if you don't do anything, it'll be the unweighted mode that runs. You will have to actively configure it to run in the weighted mode. And so be mindful of that. And there are a bunch of other configuration options that you could set completely weird values for. You can have super high tolerance or a super low tolerance, and the algorithms never go below that tolerance and never stops. You just run for a single iteration, and then you're not gonna, and it'll produce a result, but is it useful? Probably not. So keep trying out different values for the configuration options that exist and find the ones that actually produce the best results in your case. Don't just trust the output immediately after you've got it. And speaking of that, I ran my algorithm twice and I got different results. That's something that you might think will reduce confidence, right? There's a bug here, or this algorithm doesn't make any sense. Why would it, for the same data, do different things? Typically, algorithms will not do this. Most of the time, if this happens, it may indicate a bug, but there are cases where this can be expected, so it isn't always wrong. So keep in mind which algorithms that are stochastic, meaning that it uses a heuristic that is non-deterministic, as we wrote on the slide. Essentially, it means the algorithm comes to a point where it has to make a decision. And in order to make the decision, it uses randomness. It rolls a die, and it either goes right or it goes left. And the next time you run it, maybe it chooses the other direction from the first time. So it just works like that sometimes for some algorithms. So keep in mind which ones have this sort of behavior built in. It doesn't have to mean that the results are wrong. It just means that they are different. If you do find for algorithms that aren't indeterministic in this way, that they are producing different results every time you run them, maybe reach out to us and we'll have a look at it. Of course, it could be a bug. Another source of this indeterminism behavior is concurrency. So in order to optimize the algorithms, we want to make use of multiple CPU threads and run in parallel. Now, this means that the CPU threads might execute not equally fast, so we can't control, unfortunately, whether a particular thread will finish faster than some other thread. And maybe there's a race condition, like maybe one thread comes into the graph and says, tells a node, you should belong to this community. And then another thread comes along and says, no, you should belong to this community. And whoever gets there first or last is the actual choice, because there was an equilibrium and we just had to resolve the ambiguity. Neither is wrong, but they do end up being different. Moving on then, I get different results when I run my algorithm with different X. This comes down to configurability again. And this is typically intended behavior. So the mistake here is more in the expectation than with something that was actually done by the user, by you, essentially. But there are some of the configuration aspects that I'd like to call extra attention to. Some algorithms are defined, only well-defined over undirected graphs. So by default, graphs in Neo4j, property graphs, as we view them, they are directed. So the relationships point starts in its source node and moves connects to the target node. That's the direction of the relationship. Some algorithms, they aren't defined like that. They are defined theoretically as an undirected graph. In order to make that work, we have this orientation undirected configuration option that you can use in your graph projection for native projections. And this controls how many edges are essentially in the graph. That's how we implement it. We point in the relationship in both directions. This will have a great impact typically if you change this between your runs, and will definitely produce different results. You can also collapse parallel relationships. So you have a pair of nodes and it has multiple relationships between each other. You can collapse those sometimes into a single relationship that represents the set of relationships. With the single aggregation that is exemplified here, we'll just take one of them as a representative of the connection. You can do other aggregations like a max or min value aggregation, where you keep a property based on some criterion. And this will also change the way the algorithm behaves. It can do. Other things like max iterations and tolerance, I already mentioned them. They control when an algorithm stops, when it considers itself done. So I've now used up all of my iterations, which is configured by the user, and there's a default value for every algorithm for it. Now I can't run anymore, even though my sort of built-in check for convergence hasn't been met. And that's controlled usually by tolerance. So you can make it halt earlier or later in its algorithmic process by using these values. Sometimes we'll have to use one, sometimes the other. And then finally, the node labels, the relationship types, configuration options, they're used as this, we call this a graph filtering. So when you've projected your memory graph, you can add multiple labels and multiple relationship types into it. And this is optimal for performance reasons to do it with one big graph. And then you can sort of use different views of that graph. So maybe you have person nodes in it, and you have nodes relationships, you have loves relationships, and you have hates relationships, for example. It's a bit of a hostile example, perhaps. But then maybe you want to view this graph only through the nodes relationships, and you can use the relationship types key to configure that. And when you do use these, the graphs that the algorithms run over will be different through this graph filtering feature. So keep that in mind. This algorithm has literally been running for 3 months. Yes. Unfortunately, some algorithms just are very expensive to compute. We generally try to prefer algorithms that don't extend into super long running times because we want them to scale really well for really large graphs. That is a design characteristic of our library, that we want them to work really well for very large graphs, which means that some algorithms, although useful, we don't really consider them as high priority as you might otherwise think, because it's not going to ever work on a billion nodes just by its theoretical nature. In algorithmic science, we talk about this concept called NP completeness, which is essentially a classification of algorithms that are very computationally intensive. They are infeasible to solve on any sizable inputs. Betweenness centrality is one algorithm that we know is very, I don't think it's NP complete, but it is very expensive. And node similarity is also very expensive. So whenever an algorithm is very expensive, we try to give you configuration options to control how much time you will need to see it converge or even finish. So here I think we exemplify a few of them, like top K, top N, degree cutoff. They are ways that you can reduce the size of the problem for node similarity. So you don't compare all the nodes to all the other nodes, for example, or you only store a couple of those results per node with the top K. These are ways for you to sort of reduce the running time. You can check progress in the log to see that the algorithm is actually still doing work. It reports another percent and then another percent, etc. You can break up the problem, and this is usually a very good idea if it can be done. So sometimes you have a really large graph, but it's actually only some portions of that graph that represent the interesting parts. And those interesting parts, how can you know in a billion size or tens of billions of nodes, how do you know which ones of them are the interesting ones, or even how many? Unfortunately, there are some really fast algorithms that can give you rough answers to that. So WCC is very fast. If you run that, you can find immediately that only a small percentage or a small portion of the graph belong in some communities. And then it sort of breaks this graph up into multiple sets that can be then processed with a more expensive algorithm subsequently. So WC is a cheap algorithm. It can divide the problem up for you, and then these bite-sized problems can be processed in reasonable amounts of time by some more sophisticated algorithms. There are also some approximation algorithms in our alpha namespace here. Call them out betweenness sampled. It does betweenness centrality, but only for some of the nodes. And it is with the approximation methods, they aren't going to give you the highest quality results, but they might give you any results in a reasonable amount of time instead of waiting forever. So it still could be useful. My algorithm didn't run because of the memory guard. Right. So the memory guard is a feature we've installed we built into the library to prevent your whole database and system from crashing. So we make an estimation. This is also a good feature in the algorithm in the library, that you can estimate your algorithm before you actually try to run it to see how much memory it's going to consume, or that it expects to be consumed, or range at least. And if we actually do one of these estimations before the run, and if we see that there's a very high likelihood that the run that you're about to do is going to exceed the memory boundaries and might actually crash the system, then we're going to forbid it. However, the system is a system and you're a person, so if you can sometimes know better, and if you do, you can use the sudo configuration parameter to override the memory guard and allow the operation to execute anyway, with a high likelihood of it failing. But if you're better than the system, then you are. So good luck. The JVM went out of memory. This is where you could end up if you use the sudo mode. Unfortunately, you can end up here anyway. The memory guard is not perfect. This is always a challenge with very complex problems or very big problems. You need a lot of memory. You need it in memory in order for it to be fast, and then you need a lot of memory because your problem is big. These aren't recommendations to try and resolve it when it has already happened. It's too late. Then you have to restart your database and restart your JVM. But you can try and prevent this from happening by making sure to keep track of the memory usage in your system. So the graph catalog is a major feature in the library. It hosts graph in an in-memory optimized for algorithm state. Don't hold graphs that you don't intend to use there. Drop them when you're done with them, or otherwise, you don't need them. Drop them out of the catalog to free up memory. Similarly, you can drop out, you can remove properties and relationships from already existing graphs in the catalog to reduce the size of them, free up more space for the algorithms to run. And for some algorithms, you can use configuration options to allow them to use less memory as well. So that marks the end of these experience problems and recommendations. Moving on to some general guidelines, do's and don'ts. So for configuration, right, we really recommend using the memory estimation functionality. It can not only to try and find out how much memory you'll need, that too, but also to get an understanding of which algorithms are actually the most memory intensive and which configuration parameters affect the memory estimation. So how can you best configure them? And it allows you to understand more of the way the algorithms work. Try to configure Neo4j to use as much heap as possible. Again, going back to the memory question. Use the DBS, use the configuration option. You can read the documentation too. You don't have to remember it from this slide. To really set the heap as high as you can for your system. Conversely, in general Neo4j deployments, you're advised to make the page cache really large to fit your Neo4j store on the page cache. With GDS workloads, it's different. You can have a fairly minimal page cache configuration and beef up the heap instead, because that's the way the GDS library operates right now. Don't run algorithms on a core member of a cluster. Actually, don't run it on a cluster. There are issues with that. We might make it work in the future, but it doesn't really work really well on a cluster right now. So try and avoid that. It can lead to weird circumstances. But if you do run them on a cluster, try to run them on a read replica so that your core members aren't completely overwhelmed by the resources that they're running the algorithms claim. The algorithms are greedy in that way. They try to take all the resources of the system, but your core members might not like that. Projections. So when we project the graph from the Neo4j database up into main memory, you get to choose what to project. And the less you project, the less memory is used. So only project the nodes and relationships that you actually plan on using. And we have a star value, a star projection, we call it, and you can project everything from NIF database up to memory with very little syntax. It's very convenient. It's not recommended to be used in production. Don't use it unless you're just trying things out. It's much better to name your labels and relationship types. The star is only there for convenience for the most simple use cases. Similar for cipher projections. They might seem really nice when you have small graphs. You don't necessarily see the difference in performance with the cipher projection and the native projection. But when you get up to larger graphs, hundreds of thousands of nodes or millions or billions of nodes, the cipher projections will not give you the same level of performance as the native projections. So try and use the native projections for production purposes is our best recommendation here. The catalog. Yes, this is a central feature in the GDS library, and this allows you to project graphs and name them and manage them in a graph catalog, in the graph catalog. This is really good. It allows you to separate the sort of the step that is projecting the graph or loading the graph from the actual execution of the
my microphone went off, but I'm back now. So the catalog, right? Try to use it, but don't store things in there that you don't intend on using anymore. Drop graphs that you don't use, and it's better to have one large in-memory graph than having multiple small ones for memory optimization. That's the way our memory compression schemes work best. And don't use the catalog for one-time algorithm execution. You can use the in-memory. You can use an anonymous graph projection, as we call it, rather than using the catalog. That also works. But if you do that, then you're sort of doing everything in one go, which can be convenient, but it can also sort of make it harder to trace back where something goes wrong, if it goes wrong. For algorithm execution, use seeding if you can. Seeding allows you to pick up from a previous algorithmic run to move on to the next one. Threshold is good to use to reduce the size of your problem. Use tolerance and try out different concurrency settings to find out what works best in your deployment. And try to stay out of anonymous graphs for reasons of error tracing, like I highlighted previously. Try to run one workload at a time. This is sort of single user mode. We assume that there's only one person using the system at any point in time. This is because it really uses all the resources, so there isn't much room for anyone else to use the system at the time when you run deployments. But you might be using the system at other points in time for other purposes. And in that case, try to not overwrite that data. So avoid writing into properties that you use in production. But in general, try to have a separate system for your algorithmic runtime that leads to the best results. So you have a separate sort of sandboxed system where you do your algorithmic runtimes, and then don't mix that with your transactional workloads. right? This is more on the single user mode, right? For example, your user could remove a graph while the algorithm, one user can remove a loaded graph while the algorithm is running. That can lead to very strange situations. So try to stick with the single user mode and only allow one set of operations at a time. Also, if you parallelize running algorithms, the algorithms in themselves are parallelized. So they will try to use all the resources of the system. So if you think that, well, maybe I can run these two algorithms at the same time, that things will become faster, but then they will just compete for the CPU, and actually it will probably slow things down overall. So it's better to run them in sequence. And transactionality, right? So the GDS library isn't fully transactional in that way. We load the graph, to project the graph from multiple transactions for best performance. This means that if the graph is changing during the time that the graph is being projected, it might end up, it's different transactions sees different state of the NeoFJ graph. So try to have it constant during the time and not have other things going on at the same time. And when we write back, we find a good batch size. We write back in batches of 10 to 100,000 things. This works really well for performance again. However, if something fails, it might mean that rollback of everything is not going to be possible in an atomic way. Usually, algorithms can be recomputed and you can recreate those results. So hopefully, most of the time, this won't be much of an issue. But it needs to be kept in mind, I think, for when things go wrong. And with that, I'd like to send it back to Merrily. I think I'd like to thank you for listening in. And yeah, you can find us on our GitHub repository, newfday/graph data science. This is where we developers hang out. And we're happy to receive your feedback.
Thanks, Matt. That was great. Some great tips in there. And I think my favorite is I'm going to start using apples and pears instead of apples and oranges. So now we're going to take some questions. So if you'd like to submit a question, go ahead and put it into the questions tab on your console. We are running a little bit long on time, but we do have time for a few questions, and we've had some that have come in during the presentation. So I'm going to start here. So Matt, here's a question for you. I saw alpha in a few of the slides. What does that mean?
Right. Alpha, right. So in our library, we've divided algorithms into one or three tiers. There's the alpha tier, the beta tier, and the production quality tier, where production quality is the highest tier. That is the tier that we recommend you to pick your algorithms from, especially for production use cases, production purposes. The tiers indicate the maturity of the implementation. It has all the execution modes. It fits well with the general API. It's optimized for runtime and memory footprint, etc. And the other modes contain algorithms that we think might be useful, but we want to sort of move it out there for you to test it out. And if you really want it to get the best attention from us, then we'd like to hear your feedback from that. So that's sort of what the alpha means.
Great, thank you. Okay, here's another one. Let's see. In the slides, you mentioned execution modes. What are they?
Right, so the execution modes, every algorithm, at least in the production quality tier, has 4 execution modes. I think, well, it's 4 at this point in time. There might be more in the future. Stream, write, stats, and mutate. And the different execution modes, they make the algorithm behaves the same, but it's about what it does with its result. So the stream mode, it returns the result as a table, usually streamed back over the driver connection to you directly. It doesn't touch the NeoFJ database at all. The write execution mode, it does exactly what the stream does not. It writes everything down to the Neo4j database, usually as a property or as new relationships. And then it returns a single row of summary information on what happened and some statistics. The stats mode will do what the write mode does, except for the writing back part. So it will compute the algorithm and give you the summary statistics, but without any side effects. And then the mutate mode is also a version of this. It will return you the summary statistics. It will not write to the Neo4j database, but it will mutate your in-memory graph. So in your in-memory graph, you will now have new properties or new relationships. And depends on your intended use case, which of the modes that will work best for you.
Great, thank you. Okay, we're going to take one more question. And again, if your question wasn't answered live, someone from the Neo4j team will reach out to you directly. But let's go ahead and take this last question. Here we go. What if I don't have my data as a graph already? How can I test the library?
Right, so very good question. So for new users of Neo4j, there is a browser new users of the library, probably is best. We have a so-called browser guide available. And you can use this from Neo4j desktop or Neo4j browser. And you just type in :play space graph dash data dash science. And it will give you sort of a slideshow, a guide through importing some data and trying out some of the production quality algorithms. I think it's Game of Thrones data set that we have for that one. There's also a generate as a beta feature, GDS beta graph generate, that you can use to generate a random graph into memory, just to see what running the algorithms will look like. Of course, that one will not help you a lot with actual results. You'll have to have actual data, but it can give you a sense of where to start.
Great, thank you so much. And thank you everyone for joining us today. We hoped you enjoyed this first iteration of Connections. We're looking forward to doing more. Thank you again, Mass, for spending time with us, and everyone have a great day.